I'm going to tell you a bit about the work we do as a company, as a startup, Finres, and mostly focusing on like this facilitation of resilient decisions in the agricultural sector and therefore investments. Just for a very quick introduction, I've done my doctoral studies in Germany at the Potsdam Institute for Climate Impact Research, where my PhD was focusing on integrating climate risk and macroeconomic projections. During that time with PIC, I was seconded to the World Bank for 2 years, and then afterwards I worked 1 other year with the World Bank, also focusing on integrating climate risk, but this time on development investments. And then afterwards, I spent another 2 years doing exactly the same thing, like integrating climate risk, but this time in agricultural investments for the International Fund for Agricultural Development. So I have both hats in a way, this scientific understanding of like the models, the climate data and all these kind of things, and how this is used or not used by development banks in that case, but also progressively more and more private investors in making the decisions on adaptation and agriculture together. And this is what I'm going to tell you about, and I'm going to tell you a bit about what we do with Finres, which is like trying to build a stronger bridge between the scientific community. So like I would like to say you at INRAE and also IPSL and all the different institutions, with all the great work that you're doing in terms of scientific research, in terms of like new discoveries and findings, and how we can facilitate the sharing of this information in a format which is useful for investments and decision making. So the outline of my presentation is as follows. I'm going to talk a bit about the context of why we set up Finres and why this makes sense, but I guess we all agree on the context. I will talk a bit more about the financing side. I will talk about private investors. I guess this is, everyone talks about it, but everyone says we need to enable private investors when it comes to adaptation, but we don't really know how, and I'm going to tell you the approach that we're using. And then I'll get more into the scientific part of my presentation, into prioritization of adaptation options. And then the conclusions, and like very briefly on what we do with Finres. Don't worry, it's only it's a single slide. I think the main context, if I can say, is this one. It's like by 2050 we need to feed 10 billion people. So like 9.6, 9.8 billion people according to the UN by 2050. But what we see at the same time, and to feed this 9-10 billion people by 2050, we basically need to increase yield by 2.4% per year globally. Changing diets, more people means we need a lot more food available on the planet. Because at the same time, what we've seen over the last, I think, 5 or 6 years now, according to FAO, is that food insecurity is rising on the planet. So we've done like significant progress over the last 20 or 30 years. But if we look at the last 5 years, it's actually increasing. So we have more people food insecure. That shows that we're actually going into the wrong direction when it comes to providing food to everyone. And then on top of that, on top of this demographic trend, we have a climate trend that we need to add to this consideration, which is the fact, and it's a paper by Chalinor in 2014 that says like for every degree of warming that we add, we actually reduce, or like we approximately reduce yield by about 5.3%. So we have two opposite trends. On one side, we see that we clearly see that we need to increase yield. On the other side, if we don't do anything, there will be less food available as a consequence of climate change as a response to yield. And what we can see here is, and I guess we all agree on that, is that we need for more effective climate change or climate adaptation, like to be implemented like faster and more effectively. And I think effectively is a very important word here. And here it's a thought experiment, I would like to say, on this question of money and financing for adaptation, because adaptation doesn't come for free. Like there are a few adaptation options which come pretty much for free. Like for example, like crop shifting, it's not too expensive. Delaying a bit the crop calendar doesn't come for too much money, but there are like other adaptation options that comes for like a significant amount. Like we could think of irrigation, net shading, windbreaking, whatsoever. It comes for a significant amount. And if we look at the estimations, available, and we have to take it with a big grain of salt because it's a lot of assumptions underlying this estimate. But what we see is that by 2030 we would need at least $300 billion for adaptation globally. So this is what is currently being said. If we take like a bit more precise assessment, and this is an assessment by Masson de Croze in 2019, they only looked at Africa and the agricultural sector and how much this would cost to adapt the sector. It would be about $30 billion per year by 2030. So we see that the scale of the financing that we are talking about is very important and very significant, especially if we compare it to the amount of funding, and it's just as a matter of comparison. If we look at the amount of funding that we are currently disbursing every year in terms of development aid, for example, and every year we spent about like 150, 160 billion. It's stagnating. It has been stagnating for the last few years. But just to show, we will need to at least double that amount just to deal with adaptation. I'm not talking about like any other like development investments. I'm just talking about like pure adaptation investments. So we clearly see that we have a widening gap, and we are going to face a widening gap in the coming years. And not to be too bold on my statement, and I guess you all understood that, is if we just stick to traditional public sources, like the way we are currently doing investments into agriculture, like public subsidies or like international transfers of funding, it's clearly insufficient. It's clearly insufficient to meet the needs of when it comes to climate resilience. And what's going to happen is that we won't be able to catch up on the trend, this increasing 2.4% per year the yield to provide food for everyone by 2050. So that's a bit the context in which we're evolving. And I had the chance through my work, especially with the World Bank and also with IFAD, to not only to meet with public investors, but also to meet with private investors. And when we talk to them, also when we look at the literature, of course, there are two key needs that emerge from discussions and also from the literature. The first one is that we need a better risk evaluation. The main problem that they are facing is that like they don't really know what are the risks they're facing, the levels, the frequency, and all these kind of things. Mostly because most of the models that we are using are not really well able to replicate the current climate or like the current losses in the climate. And this is also the reason why you've seen like recently in the past few years, a lot of like, I would even like startups and new like climate analytics companies that are focusing on like providing and actually helping all these insurance companies and the banks remodel risk and reevaluate risk for to get a better information when it comes to the risk of their portfolio and also their clients. It's all these TCFD discussions and so on at the international level. And the second thing is improved risk reduction. What we see in the agricultural sector is that risk is very high. It's maybe less the case in France than it is in other countries. If you look at, for example, at Tanzania, it's a country with which we are working. Interest rates in the farming sector or like for agriculture is 25%. 25%, it's there is, of course, we have to reimburse the central bank, so it's about 8%. There is, of course, a bit of benefits made by the bank, but like the bulk of this 25% is actually the risk that the bank faces when they give out a loan to a farmer. So this is the reason why like we need to provide a better risk evaluation, but at the same time we provide a better risk evaluation, we'll also be able to provide risk reduction measures. And not just insurance, which is a risk transfer, but also risk reduction measures, meaning adaptation. And I guess you're very familiar with that field, so I'm not going to tell you something too strange here. There are two key issues to address when we are thinking about like risk evaluation and risk reduction. The first one is the data quality and the data availability. Of course, we work in countries like in Africa, so sometimes it's very complicated. We don't have the proper yield data. We don't have the proper climate data. Just an example, I think this is for Cameroon. We have 3 weather stations available. For the whole country, we have 3 weather stations. And I think the country might be as big, if not bigger than France. And with like very significant climate from the north to the south, east to west. But we have 3 weather stations. If we look at yield data, we might have them at some resolution, like maybe the yearly resolution, or like, sorry, the country resolution, for example, in the FAO database, or like some of the statistics. But looking at more disaggregated data on a regular basis is more complicated to find. And then also there is this overall reporting quality. it's very fine. It's sometimes very hard to judge the quality of the data. Even the climate data, sometimes it's not like reported every day. So we don't have a precipitation of one day, but we have a precipitation for 2 days within a day. So like all these kind of issues that actually seriously affect the data quality and the data availability in our field. And then of course, and I would say it's my favorite one, this is Instanti. Like it's all over the place. If you look at the ergonomic system, I'm not sure there is more uncertain system as the ergonomic system, but it's so important to all of us. And if you look at the different layers of instances, I would say first you have like the ergonomic coefficients and parameters that feeds into the crop model. The best example of that, and I will maybe talk a bit more about that later, is like the KY coefficients. So like how we transform the water stress into yield into the crop watt from the crop watt model from FAO, the same for the aqua crop model, and I think this is called now WP, water productivity. And then, of course, the past and future climate. I talked a lot about the past climate, but we have the same issues with future climate. We have a direction, a long-term direction of where we are heading into, but like depending on the RCP we are going to use, depending on the model selection, depending on the way we are going to interpret the values from the ensemble, we are going to find significantly different results. We have also instances there. If you take the soil structure, the soil runoff, the soil wilting point, the field capacity, the carbon content of the soil, also a lot of instancy in that area. Evapotranspiration is the same. Which equation you're going to use is also going to affect the type of results. Would be best if we had like lysimeters available all over the planet, but unfortunately this is not the case, and this is the same for the technologies or the measures we could use. We have some good idea of like what could be the effect of a net shade, for example. We have some kind of an idea of what is the effect of agroforestry. We have some kind of an idea of a windbreaker, but all this information comes with a range. We don't have a definite, clear, unique values for all these parameters. That makes us evolve in a massively uncertain environment when it comes to making a decision. So first we have poor data quality, or like complicated data quality. I wouldn't like to say poor, like we have complicated data quality, or like difficult to qualify data quality and availability. And on top of that, we have very high instances for all the different parameters. And then recently we just like for our own understanding, we try to count the number of uncertain parameters in our models. And we arrived between like 70 and 100 parameters that we cannot give like a single value, but we can only give a range of values for the different parameters. But luckily, despite this instances and this problem of data quality, we're not the first ones to think about these issues, and we're not the first one trying to make a decision out of that. There are methods available to deal with this, and there are two main methods, or like the result is what we call robust decision making. And of course, decision making and the deep instanti, which are the two methods that we are looking into and using in our modeling. So the first one is like when it comes to robust decision making, and clearly it shows that like just focusing on having the best prediction is insufficient, because we will never get the best prediction. We don't know what's going to be the weather, the 2nd of July 2031. Unfortunately, we don't know. We expect it would be between this value and this value, but like even for a day, we wouldn't know. We would say like within this month or within this year would be between this value and this value. So actually, instead of focusing solely on the quality of the prediction, or like the accuracy of the prediction, we should rather focus on the decision, the outcome that we are looking after. And in our case, this is a decision of investing or not investing, and in what type of technologies. And the question that we're asking ourselves is not what is going to be the yield in 2031. The question is what type of measure or what type of investment will yield positive returns in all the possible scenarios that we could face into the future. Is it going to be RCP 4.5, RCP 8.5? Is it going to be the model from EPSL? Is it going to be the model from like CN, like from the UK? Is it a model from whichever place? Are we sure that we are going to yield positive returns, whatever happens? And what is the probability that we yield positive return? And this is called a robust decision. EconAdapt, so it's a Horizon 2020 project that gathers like a number of universities across Europe, define what is a robust option, which is has the ability to to be effective over a range of possible future scenario conditions. So it's exactly what I was explaining you, like we don't really know what is the future, but we can define the future conditions, the possible future conditions of the future. And then here I explain a bit more like what is robust decision-making and decision-making on deep Instanti. I just want to focus on the second bullet here, which is like robust decision-making. This is from a recently published book by Lampert. Lampert is a bit the pope of a discipline, or the father of a discipline of robust decision-making and decision-making on deep Instanti. And he says it's a set of concept, processes, and enabling tools that uses computation not to make better prediction, but to yield better decisions under conditions of deep Instanti. So I think you locate where we want to look into, and I'm sure now you're all thinking about all the results you get from like all your modeling, and you think about the range. What does this range means actually when we make a decision? And this is exactly the type of things, this is exactly the type of range that we're interested in to come up with a decision when it comes to adaptation. First, define the yield, and then looking into the adaptation options. And then just to add a bit more complexity, because we thought it wasn't enough, the situation that we're actually facing is not a situation of just Instanti, it's a situation that we call of deep Instanti. For one of the three reasons that you see in front of you is that first, we don't really know what type of models shows best the interactions between the different variables. So it's one of the issues that we are facing because we're looking between the climate, the crops, and also the technology modeling. So like these are like three different type of modeling that we are facing, and we don't really know exactly what is the interactions between the variables. The probability distribution is not fully known, and there is uncertainty within the probability distribution of different parameters, and this is typically the case of climate. Depending on type of models, type of scenarios that we are going to use, probability is going to be different. We can define it, but we can't define it for all the climate together. And also the value of the desirability of alternative outcomes is something we can easily quantify or like assess, because people want to have access to food, people want to have like a stable food system whatsoever. So this is not met, but like actually the conditions 1 and 2 are met when it comes to robust decision making on the deep Instanti. So this is the framework that we use to make our decision. As you see, it's more a computing type of things, less than an algorithm or whatsoever. It's more a computing approach where we are going to do a lot of simulations to see whether or not an option or a measure will have positive return in all the different scenarios and at which level of return. And as I guess you understood, like the key research question, I call it research and development question, because for us, it's not just a question of research, it's also a question of implementation afterwards. So like, it's also the development part. We are a startup by the end of the day. It's how can the existing data sets, so be it like the statistics office's data, be it like the ERA5 data, the CHIRPS data, whatsoever, like the spam data when it comes to yield and so on and so forth, combined with robust decision-making and deep decision-making on deep Instanti methods, can be used to facilitate to facilitate adaptation decision-making in the agricultural sector. So this is the overall question that we came into. This is a question that I was facing, like that I've been facing when I was with World Bank, when I was with the UN, with IFAD, when I was facing like all these investments and we needed to make decisions. But I knew we had enough information, we had enough data, we had enough methods, but like it wasn't put into a framework that could be directly used to make a decision. And then when it comes to prioritizing adaptation, I don't know if you are all familiar with this, but currently I would say there are three main approaches. There is one that I ignored on purpose because it's very qualitative. It's called multicriteria analysis. So basically you gather a number of stakeholders and they're going to rank for different adaptation options based on the number of indicators. So this is the first approach which is being used. And then, but I think currently, and it's what I've seen like in quite a number of publications currently, like the main approach is using economically predefined cost-benefit ratios coming from the literature. So someone is going to do a massive assessment. So for example, you have a climate smart agriculture compendium developed by CFAS and CGIAR, where they did exactly this job of looking at the cost-benefit ratios of adaptation options. And then they multiply the decrease in yield by this adaptation option, which is going to increase yield, and they look at whether or not one is going to compensate for the other. The advantage of that is super quick, it's super cool. in a few minutes, I would like to say you can get results. You get the projections from EasyMIP for agricultural production over the next 50 years. Then you take your measure, your cost benefit ratio, and you see whether or not you have a positive return. It's amazingly fast. It's very good. The problem is that it totally misses the context. And I'm going to give you 2 examples of missing the context. The first one is like, let's say you have a benefit, the cost benefit ratio for windbreaking. But what happens if you don't have, or the area that you are like implementing your measure doesn't have wind? Why would you do windbreaking? But the cost benefit ratio would be given by the model, would be given by the database. On the other side, if you take a very windy or dry wind country, typically like Burkina Faso or like Niger, where you have like a very strong drying wind, the cost benefit ratio of a windbreaker would be significantly different, or like significantly higher. So in that way, it misses a bit the context, these predefined cost benefit ratios. And the same, if you think of drainage, in a sandy soil or in a clay-based soil, the cost benefit ratio on one side is going to be negative because it's fairly not useful if you think of like a sandy soil. On the other side, it's extremely necessary when you think of a clay-based soil. So like the cost benefit ratio wouldn't be the same. So it's what I mean by the limitation of not missing a bit the context. And then this is the approach that we developed, that we've been implementing in our model. So instead of putting the measure on the yield, or like on the effect on the yield, we put the measure directly into the agronomic model. And you have to think of, for example, like in your agronomic model, you have like soil evaporation, you have the water requirements for the plant and all these kind of parameters that do depends on a number of climatic parameters. So for example, if you take like the example of net shading, it's going to reduce radiation. But radiation is a very important parameter of evapotranspiration, at least for the Penman-Monteith equation. In the same way, if you think of the net shading, is also going to reduce the temperature under the shade. So reducing the temperature under the shade could, for example, result in the crop not meeting its optimal level of temperature and still keeping into this range of temperature. The same for soil covering, it reduces soil evaporation, so it's KE in the crop wet model by a number of percent. So it means you need less water, you need less irrigation because you're going to keep more moisture in your soil over time thanks to soil covering. So the idea is like instead of having the measure on the yield, we have them directly integrated where this is meaningful and relevant in the crop model. Clearly, the advantage of that is that it's extremely specific to the context. It allows for more adaptation options and also their combinations. So this is clearly one of the advantages. The key limitation here is that it requires agronomic modeling. It's not so easy. And also it requires a selection of the agronomic model because there are like quite a few. We don't have crop models for all the crops available. And there are these are a few of the issues that comes with crop modeling, but also like we have this issue of heavy computing and data mining because we don't have all the data available and it requires like some significant computing. And then also like following on what we mean by adaptation, because like last week we were talking about, I think or 2 weeks ago, we were talking about adaptation, or 3 weeks ago, I don't remember which Sealand webinar, we were talking about adaptation options. And here I wanted to put like, what are the adaptation options that we're looking to? Because last time I heard crop shifting, change in the crop calendar, and also irrigation. And I totally agree with that, but I don't think it's the only options. There are a lot more options that we can look into. And here we try to list a number of categories of adaptation options. They're not all here. And I'm sure there is a lot more actually in terms of categories. For example, climate information is not there, that are relevant for the farmers. And here you have like crop shifting, we talked about it, micro harvesting. It's used a lot in the Sahel countries. For example, like we are going to dig a bit deeper, like this is the Zai or the half moon 2 million technique. And in the Sahel, we have a soil covering. So like using residues, or using paper, using plastic, but on purpose, we didn't put plastic in our model. We have improved irrigation because we can irrigate with a hose. We can irrigate just with precipitation, but we can also irrigate underground with drip irrigation. So you see like you have quite a span of options available. For shading, it's the same. Shading could be done with agroforestry, but it could also be done with a net. But the net can have different colors. It can be at different altitude, heights over the crop, and it's going to yield to different physical properties and hence different reactions of the plants. Windbreaking, The same could be a natural one, like nature-based solutions, as we love calling them at the moment. So just planting trees, it's called A in French. I don't know what it's called in English, unfortunately, I'm sorry. And we also have like the shading house. Basically, we put the shading plus the windbreaking together and we create a shading house. And of course, in the end, we have the risk transfer. For all the things we cannot cover, we can transfer the risk to someone else. So these are the different options that we are looking into. And luckily, I would like to say, there are a number of countries on the planet that done a lot of work on some of these measures. And there are two countries especially, like it's Israel, especially when it comes to shading and shading houses. And the other country is actually China, which over the last, I don't know, 10, 20 years have been doing a lot of efforts into that direction. And I also like, for example, shading is a very big thing currently in China for our culture. So we're very lucky in our like thinking new things, but there were a lot of publications available on, for example, the effect of net shading on evaporation from the ground, on temperature, and so on and so forth. And I will tell you a bit more about that later. Or later, very quick. It's a two-step approach that we use. We used first like yield estimation, and then we look into investment prioritization. I have 4 minutes left, so I'm going to be super quick, but I'm sure you will have the presentation online afterwards. Here's a model definition that we used to calibrate. We use this Bayesian hierarchical calibration to calibrate our model and find the best parameters for the ergonomic model, because we're not just interested in the yield, we're interested in the parameters that lead to the yield, because the parameters that we are going to use are the ones on which we are going to apply the adaptation options. So we need these parameters. We need the KC, we need the KS, we need the KE, and so on and so forth. We're not just interested in the yield. Here we use, as I was saying, this Bayesian calibration. The objective is to minimize the ratio of yield to the ratio of crop evapotranspiration from one year to another, so that we know this evolves into the same direction. What we want to isolate and what we want to avoid using in the FAUS model into crop wet is this KY coefficient. There are a lot of publications that say it's a terrible coefficient. So we say like, okay, fine, we're not going to use the KY coefficient, might not be the best. So we isolated it in the same way as we also isolated the maximum attainable yield, because it varies massively across regions. So shall we take like the yield in the US as a reference for the yield in Tanzania? Does it make sense? Like 60 tons or like 14 tons per hectare, when currently the maximum is 4 tons per hectare. So it's some of the questions we had. So we decided to isolate these parameters to find the other parameters into the model using the equations that you see here at the bottom. Then we have these different parameters. What we use here is what we call reinforcement learning. So we don't, if we're to do all the simulations to get the best results, we will need to do 10 power of 20 simulations, which is fairly impossible. Even with all the computing power available, it would take too much time. So what we do is that we are going to use this reinforcing loop where we are going to define the parameters progressively one by one, or like even like by several of them at the same time, so that we don't have to run all the 10 power of 20 simulations. But like once we get like good results, let's say 10% deviation or like 5% deviation, we stop the simulation. We say we are fine with that result, then we can move on to the next step. And then here we select the 10 best fitting sets of coefficients. It's pretty much what I was doing in my microeconomic modeling. We don't need 20 or 30 of them. We just need 10 of them so that we have a bit of also of like deviation across the projections in the past. And then we use a random forest algorithm. And I also wanted to show the random forest on the side, because I have sometimes the impression we say, oh, we use random forest and here's the results, but we don't really know what comes in and what comes out. We know what comes in, but it's very hard to understand what happened inside. So I also wanted to show you the type of results that we get. The predictors that we used for now, but because we are still testing this random forest algorithm, like in terms of results, we used the number of days of precipitation depth above 40 millimeters, because it's a very important parameter, like to know whether or not there is too much precipitation that could affect the production. And on the other side, we also look at the mean KS, so like the water stress of a plant at the different phenological stages of a plant, so that we can also know whether there is not enough water. And these are the two main predictors that we use. It's 10 predictors, so like the 5 different stages multiplied by these two parameters, so that we can look at what is the effect on the crops and defining the yield. Here at the bottom, you see like the mean average error and the root mean square error for maize, beans, and sunflower. For Tanzania, for 5 districts here that we used for the data that we had available. So here we use the data from SPAM, the data from statistics offices. The data is coming from ERA 5. Very happy to explain why afterwards. We use the data from soil grids. It's not perfect, but like this is what we had available. And we use the prices from WFP. I mean, I don't talk about prices here, but like we use the prices from WFP monthly surveys from the different cities in the country. And all this data is updatable with more precise local data. For example, like geological surveys and so on and so forth, which is available in the country that we don't have access yet. And then here's the reconstructed yield, because we had like a lot of gaps in the data. So like here's the reconstructed yield for the different regions of the country. What you see, like the line is the mean, and the points is like the different realization of the models, like the 10 best fitting coefficients. And here we had some thinking about like this evaluation of risk, trying to replicate Moody's methodology. So like Moody's, the credit rating agency, but applying it to farmers, looking into yield volatility, year to year, yield growth, the total production, and the average yield, so that we can get a better sense of like what are the riskiest, I would say, crops or type of cropping system in which regions, so that we can somehow adjust the level of risk of the different farmers, and trying to bring down progressively like these interest rates of 25% in the farming sector, which is a massive obstacle to more investments into the area. John, I've started exceeding my time. What do I do?
Yeah, can you please just like take 1 minute to finish? I don't
Yeah,
want to rush
yeah.
you,
I'm
but
just going to show you this one and I'll leave it here. Here, when it comes to, because I didn't talk about investment prioritization yet, here it's a figure that we extracted from a paper from Tani. I think is at university in Israel. I forgot the name of university. Tani is the researcher who's been producing most of the papers on that topic. It's fairly impressive. For the last 10 or 20 years, been producing most of the papers on that shading and their effect on crops, on yield, on the different crop parameters. So what we do here is that typically we look at this type of results and we look at the data underlying that. And this is the type of information that we are going to integrate into our model. So we see the effect on the minimum temperature, the effect on the maximum temperature, and then this is the type of parameters that we are going to integrate into the model. So currently, like after all this data mining that we've been doing, we have information for about 200 different technologies under the 9 different categories I was telling you about earlier. When you start combining them, it's about between 3,000 and 4,000 different measures. So like combining them means, like, for example, you're going to do irrigation under a nightshade. Typically, this could be a combination of options, but it also means you're going to pay a lot more for the adaptation. And here I put it in red just to be a bit bold and just to spark maybe a discussion. The, the modeling that we are doing is as a different mindset. We are not looking into yield maximization anymore, because we know it's not possible, or we have the impression it's not possible just to look after yield maximization, because we have increasingly constrained resources, typically the water, typically the level of temperature, and so on and so forth. And then here we somehow shift the thinking towards an optimization. And the reason why I'm saying that is because some of the measures, and I don't know if you came to that conclusion already, some of the measures that we are proposing to implement are actually going to reduce the evapotranspiration without stress. Like typically, for example, like we are going to reduce the level of evapotranspiration when we put a net shade. But also by reducing this level of evapotranspiration under no stress, we are also going to ensure, or we hope we are going to ensure, that when there is a period of drought or there is a dry spell, the plant will still have some water available in the soil. So we are going to slow down a bit the crop all the time. So when there is a drought or when there is a heat wave, there is still some resources available for the plant in the soil. And it's what I mean from shifting the thinking from like maximization, let's bring more water, to actually optimizing according to the constraints that are surrounding the plant in which we are in the environment in which we are planting the plant. And I'll leave it here, like just talking about the KPIs, like the financial KPIs on which we are doing the prioritization, because then we transform like this financial information, this agronomic information into financial information, because we know the cost of the measures, we know how much, what is the yield, we know what could be the price in the market, stochastically, we don't know the price in the market, we know the ranges of prices in the market, so that we can define some more like different financial indicators, for example, like internal rate of return, risk-adjusted returns, and net present value, so that we can make some kind of a decision. And that's it. The conclusions, and just to show you, like all this data will soon be put into an application, so that you won't have to see all these funny graphs. You can just click on the name of the region. So like this is typically what we're doing for the client we are working with in Tanzania. You put the name of the region, the district, the type of plant, the type of existing technologies you're doing, and then it's automatically going to generate a report providing you the current credit rating or current risk to the crop and farmer. And then the second step will be on like providing investment recommendations. And I'll leave it here. Thank you.